basically, the problem arises because when we're trying to estimate one equation from a simultaneous set of equations, we get a correlation between the regressor on the right-hand side of the equation and the error term. Okay? So we've got models like this, where yi equals beta xi plus ui. Then what we've seen is that if the covariance of xi and ui is not equal to 0, then the OLS estimator is what we call inconsistent. And what we mean by that is that even in large samples, the OLS estimator will not converge on the true parameter value. So the question is, what do we do about it? Well, in the previous lecture, I'd suggested one method of getting consistent estimates of the parameter was to use the method of what we call indirect least squares. And indirect least squares basically involved estimating the reduced form of a model and then working backwards from the reduced form to what we call the structural parameters. Now, the problem we saw at the end of the last lecture is that this can be quite hideously complicated to do. Even with a relatively simple demand-supply model, it involved solving a set of simultaneous equations that was by no means obvious how we solved it. And in addition, there is another problem, that with the indirect least squares method, we may not get a unique solution. If the model is what we call over-identified, if there are too many identifying restrictions in the model, then we end up with multiple solutions. And the question is, how do we get around that problem? Well, the answer I'm going to suggest to you today is an alternative estimator known as the instrumental variable estimator. And this simplifies things drastically. It leads to a much simpler estimation than indirect least squares, and it solves the problem of the multiple solutions. I'll tell you how it solves the problem of multiple solutions in a little while. Well, let's go on to the slides now. So if we go to our slide presentation here, then let's say a few words about the instrumental variables estimator. Well, basically, the first point to note is that it is an alternative to ordinary least squares. And the reason why we choose this alternative is we want a consistent estimator even when the right-hand side variable is correlated with the error term. Now, before we get into the details of the estimator itself, one thing to note is that although the instrumental variable, or IV estimator as we'll say for short, produces consistent estimates, they will typically be less efficient than the OLS estimates. And by less efficient, I mean that they will have a higher variance. So if you think about it, there are two desirable properties of estimators. One is that they should give us the correct value. They should be unbiased or consistent. The second is that they should be efficient. They should have the lowest possible variance. Well, the problem we're going to get into with the instrumental variable estimator is that while it will act to solve one problem, the problem of getting consistent estimates, it will make the other problem worse. We'll end up getting less efficient estimates. So what we'll find is that in fact there is a trade-off when we look at the instrumental variable estimator between getting consistent estimates and getting efficient estimates. And we may not always want to choose the instrumental variable estimator, even if it means putting up with some bias or inconsistency in the OLS estimator. Okay, now the other point is to note before we start is that if we consider the case of the simultaneous equations model, which is the one we were looking at in the previous lecture, then before we can use the instrumental variable estimator, we must establish that the equation that we want to estimate is identified. We can either estimate just identified or over-identified equations, but if the equation is under-identified, we won't be able to use the instrumental variable estimator. So it won't solve the identification problem for us. We must establish that the equation is identified before we use this particular estimator. Okay, so let's start off by defining what we mean by instruments or instrumental variables. Now, the standard problem is the one that we've just set out. We want to estimate an equation of this form: y equals beta x plus u, but the covariance of x and u is not equal to 0. How can we go about finding a consistent estimator? Well, suppose we can find a variable z which has the following properties. First of all, the covariance of z and u should be equal to 0. So notice how that contrasts with x. We want to find another variable z which is not correlated with the error term. So the covariance of z and u is equal to 0. But at the same time, we need the covariance of x and z not to be equal to 0. Okay? The reason why that's the case should become obvious in a little while. But just for the moment, let's assume that we can find a variable which has these properties. If we can find such a variable, then we can define what we call the instrumental variable estimator as follows. Beta hat IV equals the sum of z times y divided by the sum of z times x. Okay? So that's the definition of our instrumental variable estimator. Okay, now, first and most important, we want to establish that an estimator with these properties is what we call a consistent estimator. In other words, we want to establish that it will converge on the true value as the sample size gets large. So how can we go about doing that? Well, we can go about doing that using the standard method that we've applied all the way through when we want to assess the properties of an estimator. In other words, we take the definition of the estimator, we substitute in for the value of y, and then we look at the properties of the estimator when we expand that expression out. And I think that's worth spending a little bit of time working through. So what I'm going to do here is switch over to the display here, and then to get this on the lecture capture, I've got to switch over here as well. And I'm just going to work through this process with you to show you how we can establish that this estimator is consistent. So we've defined the following. Beta hat IV is equal to the sum of zy divided by the sum of zx. Okay? So how do we establish that this is consistent? Well, we substitute from y from our original model. So we write this as the sum of zi times beta xi plus ui, again divided by the sum of zi times xi. Now if we multiply this out, you'll see that the first term is going to be beta, which is a constant, multiplied by the sum of zx divided by the sum of zx. So the first item is just going to be beta here, and then the second item is going to be the sum of zi times ui divided by the sum of zi times xi. Now we want to ask the question, what happens to this expression as the sample size gets large? What happens to the estimator when we let the number of observations grow? So to do that, let's take this second expression here and divide numerator and denominator by the sample size. Okay? And we're going to make the assumption that as the sample size gets large, 1 over n times the sum of zu will converge on the covariance of z and u. Okay? So we're going to assume that the probability limit of 1 over n times the sum of zi ui is equal to a constant which is the covariance of z and u. So we're saying that as the sample size gets large, if we take the sum of z times u and divide by the number of observations, it will just converge on the covariance, which seems a fairly reasonable assumption to make. Similarly, we're going to assume that the probability limit of 1 over n times the sum of zi xi is going to be the covariance of z and x. So these are what we called in previous lectures regularity conditions. These are just assumptions we make about what happens to these products as the sample size gets large. So just to remind you, we call these in a previous lecture regularity conditions. I should note that these are assumptions. There may be situations in which these fail. We're not going to consider them here, we're going to assume that these hold, but there's no necessary reason why this should be the case, we're just going to assume it's the case. Now, if that's the case, we can show consistency quite straightforwardly. We can take the probability limit of beta hat IV will be equal to beta plus the probability limit of the top line here, so that's plim 1 over n times the sum of z u, and divided by plim 1 over n times the sum of z x by the properties of plims. And of course that in turn can be written as beta plus the covariance of z and u divided by the covariance of z and x. But we made a couple of assumptions about those. We've assumed, remember, that by the properties of the z variable, that the covariance of z and u is equal to 0. So the z variable is uncorrelated with the error term, and also that the covariance of z and x is not equal to 0. Now, if those assumptions hold, we're dividing, this expression has got 0 on the numerator and a non-zero number on the denominator, and therefore it will become 0 as the sample size gets large. So therefore we have that the probability limit of beta hat IV equals the true value beta, i.e. beta hat IV is what we call a consistent estimator. Okay. Now notice, this all depends on us being able to find a variable z which has these properties. Okay? So we need a variable z which has these particular properties, that the covariance of z and u is 0 and that the covariance of z and x is non-zero. We've not said anything about where we find such a variable. Okay, we've got to be able to find such a variable. Now it happens that particularly when we come to the simultaneous equations model that we looked at last week, there are some natural variables that arise that will do this for us, and they are the exogenous variables of our model. Okay, but in more general cases, it may not be obvious where the z variables come from. Okay, well, let's go back to the slides and take a look at this in a little bit more detail. So if we go back to the slides here, okay, then this is essentially what we've just done here. Sorry, I've not just got to switch over on the projector now, I have to switch over on the computer as well. So my apologies if I end up doing one and not the other. This is what we've just done. We've taken this expression here, we've divided the numerator denominator by n, we've taken probability limits, and we've shown that under the assumptions that we are making about these covariances, this converges on the true value beta. Okay, since z and u are uncorrelated by assumption. Now, what we need to do now, however, is we've established that this estimator is consistent, but we haven't said anything about what its variance will be. So what I need to do now is to show you how we can derive first of all, derive an expression for its variance, and secondly, show you the problem that I pointed out earlier, that in fact, we'll get a variance that must be higher than the ordinary least squares variance. So it will be less efficient than ordinary least squares. So just to run through the argument first of all, what we'll find is that when we find the variance of the instrumental variable estimator, the variance of beta hat IV, we'll get the following expression. We'll get sigma squared u divided by the sum of x squared multiplied by rho hat squared, where rho hat squared zx here is the sample correlation between x and z. Now, the problem with that is that rho hat is a correlation here, so rho hat squared must lie between 0 and 1. If you think about it, the correlation must be lie between -1 and +1. So if we take a correlation and square it, then it must lie between 0 and 1. So if we take this expression here, we've got sigma squared over the sum of x squared. Well, that's just the variance of the OLS estimator, but we're multiplying the denominator by a number that is less than 1. So we're reducing the value of the denominator, and therefore the overall expression must be greater than the OLS variance. I'll work this through in a little bit more detail in a minute. I just want to get the broad outline of the argument out of the way first of all. So we can show that the IV estimator must have a higher variance than the OLS estimator. And we can go a bit further than that. We can show that the lower is the correlation between x and z, in other words, the closer rho hat squared is to 0, then the higher will be the variance of the instrumental variable estimator. In other words, the less efficient that estimator will become. Okay, well, let's just spend a moment or two working through that to show where that expression comes from. So again, I'm just going to go back here to the visualizer. Okay, and we're going to demonstrate where that expression for the variance has come from. So let me just take a step back. We've got the following. We've got the instrumental variable estimator, beta hat IV, can be shown to be equal to beta plus the sum of zi ui divided by the sum of zi xi. That was one of the stages we got to earlier on. Now, it's actually extremely hard to derive the asymptotic variance, or what happens when the sample size gets large here. It's much easier if we take the rather simpler case of when the Gauss-Markov assumptions hold. Okay, so I'm going to just take a stage back here, and I'm going to assume that the Gauss-Markov assumptions hold, except for the one crucial one here, that the expected value of xi and ui is equal to 0. Okay? So we're going to assume that Gauss-Markov assumptions 1, 2 and 3 hold, but the fourth assumption, Gauss-Markov assumption 4, doesn't hold. Okay? So we'll have in this case that this expectation will be non-zero. Okay, now given that, what we want to do is we want to evaluate the variance of beta hat IV. And the variance is just the expected value of the estimator minus its expected value squared. In other words, it's the expected value of beta hat IV minus its expectation all squared. Okay? But if the other Gauss-Markov assumptions hold, then, so if Gauss-Markov 1 to 3 hold, then the expected value of beta hat IV will be the true value beta, and therefore the variance of beta hat IV will be the expected value of this expression here, all squared. In other words, the sum of zi ui divided by the sum of zi xi all squared. Okay? Now, I need to evaluate that expression, but again, under the Gauss-Markov assumptions, that's relatively easy. So if we make standard Gauss-Markov assumptions, this is relatively easy. We can write this as the sum of zi squared times sigma squared u, the variance of the error term, divided by the sum of zi xi all squared. Okay. Now, let me remind you of something that from your first year stats now. What I want to remind you of is the formula for the variance, or for the correlation coefficient between two variables. And in particular, what we need here is the square of that correlation. We need the squared correlation coefficient can be written as the sum of zi xi all squared divided by the sum of zi squared multiplied by the sum of xi squared. That's the definition of a correlation coefficient between two variables, or more accurately, the square of the correlation coefficient. Okay, and that is something you use in basic descriptive statistics from level 1 onwards. Now, if that's the case, I can substitute for this expression on the denominator here, the sum of zi xi squared. Well, if I multiply both sides here by the sum of zi squared, sum of xi squared, I can substitute that in and note that the sum of the zi squareds will cancel, leaving me with the following expression. I'll have sigma squared u divided by rho hat squared zx times the sum of xi squared. So that's just using this definition to substitute for this expression on the denominator here. Okay. Now, what we can recall as well from last semester is that the variance of the OLS estimator is equal to sigma squared u over the sum of xi squared. So we can write the variance of the IV estimator as being equal to the variance of the OLS estimator divided by rho hat squared zx. In other words, divided by a number that must lie between 0 and 1. Okay? So rho hat squared zx must lie in the interval 1 to 0, and therefore the variance of the instrumental variable estimator must always be greater than or equal to the variance of the OLS estimator. It can never be less than the variance of the OLS estimator. In other words, what we would say is that instrumental variables is inefficient. It has a higher variance. Okay? And again, you can see from this expression that the extent of that inefficiency, the extent to which the IV estimator has a higher variance than the OLS estimator, is going to depend upon how close rho hat squared is to 0. If rho hat squared is very small, so there's very little correlation, then this variance is going to be much greater than this variance. If rho hat squared is close to 1, so there's very good correlation between z and x, then it may not make much difference. So the variance may not be that much greater, but it will still be a little bit greater, provided it's not exactly equal to 1. Okay, so that's the instrumental variable estimator, and that's really a lot of the technical bits that I need to go over with you. What we're going to do now is going to move back to the slides here. Okay. And considering a little bit more detail and examples. This is an extra slide I put on before the lecture because I thought this would be a good time to actually consider an actual example rather than theory. So what I've done here is take one of the examples that we used in the previous lecture, and that's basically estimating a simple Keynesian style consumption function. What I've done is I've regressed the change in consumption expenditures, this is for the UK from 1949 to 2005, on a constant and the change in GDP. Some of you doing projects may recognise a little bit of familiarity in this. Okay? This is the kind of thing you might well have been doing yourself for your project. Well, if we do that, we get quite reasonable looking results. We get a slope coefficient here of 0.62, standard error 0.05, and t-ratio of 12.11. The reason why I've taken differences is because if I knew if I didn't take differences, I would have a lot of serial correlation in this regression. But if we look at the Durbin-Watson statistic, we see it's 1.4. It's not that low, so it's quite a reasonable dynamic specification here. But of course, as we saw in the previous lecture, we've got a problem here. If this is a Keynesian consumption function, then GDP is determined simultaneously with consumption expenditures. If you think about your Keynesian cross diagram, then consumption and national income are jointly determined. And we know if that's the case, then this will be subject to what we call simultaneous equations bias. We'll tend to get the result that GDP will be correlated with the error term in this regression, and therefore this coefficient estimate here will be biased and inconsistent. So what can we do about it? Well, what we can do is we can run an instrumental variables regression. But what should we use as an instrument? Well, what we need is a variable which is not correlated with the error term, but which is correlated with the original exogenous variable. Well, in this case, the exogenous variable is the change in GDP. Now, if you think about your Keynesian cross diagram, what variable affects GDP? Well, normally it would be some change in autonomous expenditures, such as a change in investment expenditure. Now, if we take that change in investment expenditure, it automatically has the properties we require. It's correlated with the original exogenous variable. It's correlated with national income because changes in investment will push the expenditure line up and down and will cause GDP to change. But it's not correlated with the error term because there's no reason to assume that changes in investment spending will be correlated with changes with the error term in the consumption relationship. So the change in investment is a natural instrument to use here, and that's what I've used in this second regression here, where I've used as instruments the constant and DI. I've estimated the regression equation again, and you can see that it has these properties that we talked about. First of all, it's made a difference to the slope coefficient, and we'd assume that this is now a consistent estimator because it satisfies these properties. But the cost of that has been that it's pushed up the standard error from 0.051 to 0.069, and as a result, the t-ratio has gone down from 12.11 to 9.42. So what we've got here is an example that illustrates those points. It changes the slope coefficient, but there is a cost to that in the form of a higher variance, a higher standard error of the coefficient estimate, and as a result, we've got a less efficient estimator here. That might be a good point to just take a very brief pause and ask if anybody has any questions or anything they would like to ask at this point. I'm willing to take questions here. Right. I'm also willing to carry on, so don't worry about it. So, we've identified this now. What I want to speak about now, though, is this issue of the trade-off between bias and variance. Now, you're probably all used to thinking biased estimates are good, unbiased estimates are good, biased estimates are bad. or in large sample terms, consistent estimates are good, inconsistent estimates are bad. Well, that's true, but bias and consistency aren't the only desirable properties of estimators. The other desirable property is that we should have efficient estimates, estimates with as low a variance as possible. Now, what we've run into here is a case in which there is a trade-off between bias and efficiency. And what we've got to do is find some way of looking at that in a little bit more of a formal sense. And to do that, I want to introduce a new idea to you, and that's the idea of the mean square error. So the point here is not always obvious we want an unbiased estimator at all costs. Okay? Instead, we might want to take into account the variance of the estimator. An alternative criterion which allows us to look at the trade-off between bias and efficiency is what we call the mean square error criterion. The mean square error criterion is defined as follows. The mean square error is the expected value of beta hat minus beta all squared. Now, that might look like the formula for the variance, but it's different in one very small but important way. The variance would be the expected value of beta hat minus the expected value of beta hat all squared. Okay? This is just beta hat minus beta. There's no expectation operator here. Yeah? So, what that means, however, is that we can decompose this into two bits. If we multiply this out, then what we can do is we can write this in the following way. We can write it as the sum of the variance, the expected value of beta hat minus its expected value squared, plus the expected value of beta hat minus the expected value of beta hat all squared. Okay? It's a little bit of algebra to get us to that point, but it's not actually too difficult. It just takes a few lines to work it through. I suggest you work it through as an exercise if you're interested. But what we get out of it is that the mean square error can be written as the sum of the variance plus the square of the bias in the coefficients. So that gives us a way of perhaps trading off these two desirable properties of an estimator. We want to minimise the mean square error because we want an estimator with low bias, but we also want an estimator with low variance. So what's very often argued is that rather than choose unbiasedness at all costs, we should instead choose the estimator with the minimum mean square error. Okay, now we can illustrate that as follows. What I've done here is just draw some hypothetical probability density functions for two different estimates of some random variable of interest. And for the sake of argument, I'm going to assume that the true value of this random variable is 0. Okay? Now, the PDF with the red line here, so this red line illustrates the probability density function for an unbiased estimator, because you see it reaches a peak at 0. So this is unbiased. The blue line shows the probability density function for a biased estimator. And you can see it's biased because it reaches its peak somewhere to the right of 0 here. Okay, so this is a biased estimator. However, the biased estimator has got a much lower variance than the unbiased estimator. The spread is much smaller for that PDF. What that means is that if we were to use the biased estimator, then on average we're probably going to get an estimator that's closer to the true value than if we use the unbiased estimator, because it's got lower variance. So this illustrates why unbiasedness is not desirable at all costs. Unbiasedness we may get an unbiased estimator, but we may have such a large variance that the chance is that when we actually employ that estimator, we're way away from the true value. We may have a biased estimator, but if the variance is very small and the bias isn't too serious, then on average we may get closer to the true estimator than with the unbiased estimator, or to the true value, not, okay, you know what I mean. Okay, so that's the minimum mean square error criteria. Okay, now, this example here is estimating the consumption function. We've already looked at this on the previous slides. This is essentially the model that we just looked at. This is the simplest Keynesian consumption function with a pair of equations here. Okay, we solve it out to get the reduced form for y, and that gives us the result that delta y is correlated with the error term. And we've seen just on the previous slides, if we go up a couple of slides here, that's the difference here between the OLS estimator and the IV estimator. Okay, so that slide here, oops. This slide here just really gives the theoretical background for what we did for the example a few moments ago. Okay, so in this case, the reduced form equation shows that the change in income is correlated with the error term from the consumption function. It follows the OLS estimate of the consumption function will be inconsistent. An alternative is therefore to use the change in investment as an instrument and then use the IV estimator. The change in investment is correlated with the change in income. There's no reason to think it should be correlated with the error from the consumption function. Okay, and the example we just looked at illustrates precisely that. Okay, now, one of the questions that arises is what happens if we've got more than one possible instrument? And if that's the case, then there's another related estimator that we often use, which is called the two-stage least squares estimator. Now, in fact, many statistical packages don't make a distinction between instrumental variable estimators and two-stage least squares estimators. They're essentially the same thing. So if you go to eViews, for example, you will find that it doesn't make a distinction between them. But it does raise a complication when we have more than one potential instrument. Which instrument do we choose? Well, the answer is we use a combination of them. If we have more potential instruments than there are endogenous variables, then we do the following. First of all, we regress the endogenous variable on all the instruments and compute the fitted values. In other words, we estimate a reduced form equation for the right-hand side endogenous variable. We then use that as an instrument in a second stage regression. So we take the fitted values from that first stage regression, and then we use those as instruments in a second stage regression. Okay? I think that's perhaps just worth spending one moment just illustrating what's going on there. So if again I just move back to the visualizer here. Okay. The problem is we want to estimate the following model. yi equals beta xi plus ui. Okay? And we've got this perennial problem here. The covariance of xi and ui is not equal to 0. Okay? We've got two possible instruments. Okay? And those are Z1 and Z2. So how do we use an instrumental variable estimator when we've got more than one possible instrument? Well, the answer is we use a two-stage approach, and in stage 1 we compute a set of fitted values from the first stage regression. So we regress x on Z1 and Z2, and we construct xi hat equals alpha 1 hat Z1i hat plus alpha 2 hat Z2i hat, and then we use those in the second stage of the regression as instruments. So we construct a new estimator here, beta squiggle equals the sum of xi hat times yi divided by the sum of xi hat times xi. Okay? So effectively, this is just another form of instrumental variable estimator, but one in which we could create our own set of instruments. I'm sorry, by the way, I just realised I haven't switched over onto the lecture capture there, and it probably will not have recorded me writing this down. But nevertheless, you can see it from here. This is the process by which we, first of all, create the instruments, and secondly, by which we use those instruments in the second stage regression. Okay, well, what I want to do is take a look at an example of that. So if we again now go back to the slides here, we're going to take a look at an example of this using the income expenditure model that we've talked about already. So, suppose we've got not just one class of autonomous expenditure, but two. We've got data on investment, we've got data on government spending. Either of those could be potentially used as an instrument for an instrumental variable estimator. So what do we do in order to create a set of instruments? Well, we adopt the two-stage approach. We first of all, we regress dy on a constant di and dg. And this is effectively my reduced form equation for the change in national income. Then I create a set of fitted values from this, and I've called these fit y here, and I've used those as an instrumental variable estimator in my second stage regression. So I've taken a second stage regression here where I've estimated the same equation but using these as an instrument, and these are the results I get. Okay, this is my coefficient here, 0.665. It's not a million miles away from the previous estimates, but again, you notice that the standard error is rather lower than the standard error from, rather higher than the standard error from my OLS regression. The t-ratio is rather lower. Okay, so that's an example of the two-stage least squares approach. Now, in practice, you don't need to carry out both stages manually. It's perfectly possible to do this in a single stage. What we do is when we specify the instrumental variable estimator, we just give it a list of all the instruments here. In this case, C, DG and DI, and it will calculate the estimator without actually physically doing the first stage. So most computer packages automate the process of doing two-stage least squares. Okay, I've got one further topic to cover today, which is the topic of the Houseman specification test. But given the amount of time I've got left, I don't think I've got time to do it justice, so I'm going to leave that over until the next lecture. So that's it for today, and I'll see you all